let's explore another mechanism that we can have with a ketone. And actually, an aldehyde could undergo a very similar, actually the same type of reaction. So let's say that I had a ketone that looked like this. So that's my, draw my carbonyl group, just like that. And then it is bonded to a carbon that is bonded to two other CH3 groups. And just to make it clear, I mean, there's three hydrogens off of this carbon there implicitly. But I'm going to draw the fourth bond here, which is to a hydrogen, because this hydrogen is going to be important for this reaction. Now, we know that the oxygen has two lone pairs of electrons. Let me draw it up here. And let's just imagine it's floating around in some water. And we know that in water there is some concentration of hydronium. And let's say that one of the hydroniums is right over here. So let's see, hydronium is just a positively charged. So this right here, let me make it clear. This, let me do a different color. This is what water looks like. This is what water looks like. And if water gives away an electron to a proton, it looks like this. It is hydronium, and then it only has one lone pair of electrons. It gave away one of the other electrons and its other lone pair to a proton. So you could imagine a reality. Well, it's like, hey, I could grab that proton from this hydronium, and then this will turn back into water. And in that situation, the mechanism would look like this. This electron, let me do it in a different color. This blue electron gets given to this proton if they just bump into each other just right. And then the hydrogen's electron gets taken back by what will become a water molecule. So if that happens, what do our molecules now look like? So now our what was a ketone looks a little bit different than a ketone. So it looks like this. I changed it to a slightly lighter color of green. So it looks like that. We have our lone pair over here, but we no longer have this lone pair. At this end, we still have this magenta electron, but now it is in a covalent bond with the blue electron, which was now given to the hydrogen proton. Let me scroll up a little bit. It was given to this hydrogen proton up here. It was given to that hydrogen proton up here. And then this hydronium molecule, it took back an electron, and now it is just neutral water. It is now just neutral water. It took back that magenta electron. So now it has two lone pairs again. So it is just neutral water. Now this, since this oxygen up here in the carbonyl group gave away an electron, it now has a positive charge. It now has a positive charge. But this is actually resonance stabilized. You could see that this is, or you could maybe see that this would be in resonance, or another resonance form of this would be if this guy's positive, so he wants to gain an electron. So maybe he takes an electron from this carbon, the carbon in the carbonyl group right over there. So if he takes that electron, so then the other resonance form would look like this. You would have, and let me do it in the same colors. You have now only a single bond with this oxygen up here. This carbon down here still bonded to the same carbons. And then this carbon over here, we could call this an alpha carbon. This is an alpha carbon to the carbonyl group. It still has a hydrogen on it right over there. And this oxygen, since it gained this magenta electron, so now it has two lone pairs. Again, it has this pair over there, and then it has this electron and this electron, so it has another lone pair. And of course, it has the bond to the hydrogen. It has the bond to the hydrogen. Since it gained an electron, it is now neutral. This carbon lost an electron, so now it is positive. So now this carbon right over here is positive. And these two are two different resonance forms, so they help stabilize each other. And the reality is actually someplace in between. And I could actually draw it in brackets to show that these are two resonance structures. Now, you can imagine, just as likely, and actually I shouldn't just draw this as a one-way arrow, because this guy could take a hydrogen from this hydronium, or a water could take a hydrogen from this guy. So this actually could go in both directions. Let me make that clear. This could go in both directions. You could say that they're in equilibrium with each other. You're just as likely to go in that direction as you really, for the most part, are to go in the other direction. But you can now imagine, okay, this is now turned in from a carbonyl group. This is now an OH group. This is now turned into an alcohol, although we have this carbocation here. That this does not like being positive. And so you can imagine where this electron right here being attracted on this hydrogen nucleus might want to go really bad to this carbocation. And it just needs something to nab the proton off for it to go there. And the perfect candidate for that would just be a water molecule. We have this water floating around. So let me draw another water molecule just like this. It has two lone pairs. It can act as a weak base. It can give one of its electrons to this hydrogen proton. If it does that at the exact same time, bumps into it in the exact same way, this electron can then go to the carbocation. And if that happened, and you could go in either direction. This reaction is just as likely happening as the reverse reaction. So we could put this in equilibrium. But if that were to happen, then what started off as our ketone now looks like this. It now looks like this. We have a bond to an OH group, just like this. And over here, actually, let me draw the rest of it. We had our molecule that looked like that. But now this electron gets given back to this carbocation. We now have a double bond here between our carbonyl carbon, or what was a carbonyl carbon, and our alpha carbon. So now we have this double bond right over here. That hydrogen has been taken by the water. And now that is hydronium. So let me draw the water, or the hydronium. So that water, it had that one lone pair, and then the other lone pair got broken up because it gave one of the electrons to this hydrogen right over here, and it went back to being hydronium. So what happened here? We started with a ketone. And they sometimes will call this the keto form of the molecule. And then we ended up with something called an enol form. An enol, or maybe I should say not enol, or enol form. An enol comes from the fact that it is an alkene. It is an alkene that is also an alcohol. You could even call it an alkenol. It has a double bond, and on one of the carbons that has a double bond, it has an OH group. And the whole reason I show you this mechanism is, one, just to show you a mechanism that could happen with an aldehyde or a ketone. This was a ketone, but if this was a hydrogen right here, this would have been occurring with an aldehyde. But even more, this is a pretty common mechanism that you'll see in organic chemistry classes, and actually has a lot of functions in biology in general. And these two molecules, this ketone and this enol form, these are called tautomers. And the keto form is actually the much more stable form. In a solution, you won't see much of the enol form, but these can occur. It can spontaneously, through equilibrium, get to the actual enol form. And so you could imagine these are tautomers. So this mechanism is actually called a tautomerization. And these are the keto and enol forms of the tautomers.